Alrighty, so nomenclature of epoxide. So in the last video, I kind of left off here saying that an oxirane is a three-membered ring with an ether in it, and we also call those epoxides. They're one and the same. An oxirane refers to the actual three-membered ring, and epoxide is like, let's say you have something like this, you have a longer chain and then you have the ring in it, we call that an epoxide. But you can name an epoxide as an oxirane or an epoxide. Both are acceptable. And so if we look at an epoxide, it can have up to 4 R groups, right? Because if you look at ethylene oxide or oxirane, so we call this ethylene oxide, okay? It has 1, 2, 3, 4 hydrogens, and so it can, of course, accommodate up to 4 R groups. So, I didn't even realize that ethylene oxide was on there. My mistake. Anyhow, so the epoxide can have up to 4 R groups. And it says, even though they're unstable, epoxides are commonly found in nature. You see this one here that's a sex pheromone of some kind of moth, which is kind of interesting. But this compound here, I don't know a lot about periplanone B, but I know it was a synthetic target for a few labs. In the lab that I did my graduate studies in, I think that they were interested in making that at some time after I left. I don't know if they ever followed up on it or not, but kind of an interesting compound there with 2 epoxides in the same compound. Anyhow, let's move on from there. So how do we name an epoxide? Well, there's 2 ways to do it. One is to treat the oxygen as a side group, and you use 2 numbers for the locants. Okay, so you just call it a side group, just like an alcohol or an alkene or an alkyne or anything like that. So what do? You find the longest carbon chain that contains the functional group, which is the epoxide, and you want to give the epoxide the lowest possible number. So it's a 2,3-epoxy pentane, and then you just name the other substituents. You have a 3-ethyl, and you have a 2-methyl, like this, and there you have it. You can also name it as an oxirane, and again, oxirane is a 3-membered ring. So oxygen is going to be number 1, one of the other carbons is 2, and one of the other carbons is 3. And so in this case, we have double substituents on carbons 2 and 3. So we go by alphabetical order in that case, right? We have a 2,2-diethyl and 3,3-dimethyl oxirane. So both are perfectly acceptable, and you need to know both ways of doing it. So much so that when I first started teaching this class, my boss, he teaches this class as well. And I asked him, I said, do I have to teach them both ways? And he wrote me back, yep, you do. So without further ado, let's see if we can name both of these compounds using both the oxirane method and the epoxy method. So we'll start with the oxirane method. And remember that oxirane, so I'll use oxirane. Oxirane is a 3-membered ring, and the oxygen is number 1. So if we are naming this compound as an oxirane, the oxygen is number 1. This carbon is going to be number 2 because it's got substituents, and this will be carbon number 3. So we would just call this compound 2,2-dimethyloxirane. So let's scribble that down, 2,2-dimethyloxirane. All right. And if we want to name it as an epoxy compound, in that case, we have to find the longest carbon chain, and we want to give the epoxy the lowest numbers we can. So the longest carbon chain we have in this molecule has 1, 2, 3 carbons, right? And we have the epoxide between carbons 1 and 2, right? If you're thinking, no, shouldn't you start over here, 1, 2, 3? No, that's wrong because it's between 2 and 3. I want the epoxy between carbons 1 and 2. So I have a 1,2 epoxy propane, and then I have a methyl group on carbon 2. So I would call this 2-methyl 1,2 epoxy propane. 2-methyl 1,2 epoxy propane. All right, for the next one, it's kind of similar, so I won't spend too much time on it. If we were to treat this as an oxirane, right, there's their 3-membered ring. We've got 2 aromatic rings, but remember when an aromatic ring is a substituent, we call it a phenyl. And so this would be 2,2-diphenyl oxirane. And the longest carbon chain in this compound has 2 carbons, so 1, 2. So we'd call this 1,1-diphenyl epoxy ethene. So we'd call this 1,2-diphenyl epoxy ethane. And if you're wondering, why didn't you put a locant here? Why didn't you say 1,2-epoxy ethane? You don't have to, because ethane only has 2 carbons anyway. Right? There's only 2 carbons in ethane, and so it would be redundant to put a locant in there. All right, give me a thumbs up if you're with me 50% of the way on naming these. Okay, cool. All right. So any questions on those before we move on to? All right. All right, there we go. So it's not a phenol, it's a phenol, right? So phenol and phenol are 2 very different things, right? A phenol is an alcohol. This is phenol, right? And a phenyl is when you have an aromatic ring as a substituent, right? That's what we call a phenyl. Okay, does that make sense? Phenol is a molecule, phenyl is a substituent, just like methyl, ethyl, propyl, butyl. Oh yeah, sorry. Thanks, Tiana. It should be 1,1, right? So 1, 1. There we go. 1,1-diphenyl epoxy ethane. All right, let's move on to something a little more involved. It says assign a name for each of the following compounds. Be sure to assign the configuration at each chiral center to indicate the configurations at the beginning of the name. So what we'll do is we'll just try the first one, and then we'll come back and do the other ones during the next lecture. But let's take a look at the first one. If we want to name this as an oxirane, so if we want to name this compound as an oxirane, we're going to start with carbon number. I'll be consistent with my colors. So 1, 2, 3. So we have a 2-methyl, 2-phenyl oxirane. So let's scribble that down. 2-methyl, 2-phenyl oxirane, like that. So now we need to determine the stereochemistry. Is this an R compound or an S compound? So here's our stereocenter. Right here, we have an oxygen. That's going to be group number 1. Then this carbon is attached to carbon, carbon, carbon. This carbon is attached to hydrogen, hydrogen, hydrogen. And this carbon is attached to an oxygen, hydrogen, hydrogen. And so this carbon is going to take 2nd priority, and this one is going to take 3rd priority, or this group is going to take 3rd priority. And so since the methyl group is the lowest priority and it's in the back, we can go from 1 to 2 to 3 around the stereocenter like that. We're going clockwise. And so this is an R compound. And thus we can pencil that in. We can say R 2-methyl 2-phenyl oxirane. Now, the stereochemistry isn't going to change. If it was an R compound once, it's going to be an R compound the 2nd time. And so if we name it as an epoxide, so let me just change the color here. If we name it as an epoxide, it's still going to be an R compound. Let me just erase all my notes here. So let's just delete all that, and we're going to start over. And we're going to look for the longest carbon chain. And you can see that the longest carbon chain has 1, oops, where's my pen? 1, 2, 3 carbons in it. So this is a 1,2 epoxy propane. And we've got a phenyl at carbon number 2. So we'd call this R 2-phenyl, 1,2 epoxy propane. There you go. So some of your homework then for next lecture, I'd like you to try to name both of these using the oxirane method and the epoxy method. And we'll do this on, what's today, Monday? So we'll do it on Wednesday. All right, so something to look forward to. Okay, so give those a shot yourself, and then we'll come back and try them on Wednesday. So there you go. There's a little bit about epoxide nomenclature. Again, I have a whole YouTube video that goes over these problems in gory detail. If you want to take a look at those before, I recommend it, as a matter of fact. Well, let's switch gears and get into section 13.8, get back into some reactions, some synthesis. And so we're going to talk about the preparation of epoxides. How do we make an epoxide? Well, you already know one way of doing it, right? Is to take a peroxy acid, okay, a peroxy acid, which has the formula RCO3H, all right? And there's two peroxy acids that you need to know. One is MCPBA, right? MCPBA is the classic one you learned in organic chemistry 1, but there is another one. If your R group is just a methyl group, we call that peroxyacetic acid. Both work extremely well. You do not have to know the mechanism of the epoxidation. I'm going to write that in here because I think it's shown in the textbook, but I'll just put will not ask mechanism. Okay, I'm not going to ask it to you or ask it of you, but it is shown in the textbook. Anyhow, so now that you know how to make an epoxide, something that we didn't cover in organic chemistry 1 is the fact that epoxidation of an alkene is a stereospecific reaction. So if you start out with a cis alkene, as is shown here on the top, and you treat that with a peroxy acid like MCPBA, you end up with a cis oxirane. Right, so here's your oxirane, and you see the two R groups are on the same face of the molecule, right? They're cis on your ring. Similarly, if we start with a trans alkene, we end up with a trans oxirane. You see that the two R groups are on opposite faces of the molecule. And remember, this means that these reactions are stereospecific. Cis gives you cis, trans gives you trans. They are not stereoselective, like you don't get mixtures or anything like that. If you start with cis, you get a cis. If you start with trans, you get a trans. All right? So stereospecific. Now, let me show you another way to make an epoxide that is connected to a reaction that we did earlier on. You might remember halohydrin chemistry from way back in chapter 8. Okay? In chapter 8, in the alkenes chapter, I told you that if you took a alkene like cyclohexene and you treated that with bromine and water, you ended up with a halohydrin, and that the hydroxyl and the bromine are added in an anti-fashion. And so what happens is that you can take the halohydrin, so this is our halohydrin, and you can treat that with a base and it makes an epoxide. And this is a really interesting mechanism. So I'm going to draw this compound in its chair form. It's not the prettiest chair in the world, is it? That's not much better. But anyhow, if we have the hydroxyl pointing up like this, and if we have the bromine going down like this, if we use a base like sodium hydroxide and we deprotonate, right, the oxygen to make an alkoxide, this can do, let me draw my lone pairs here. This can do an SN2 reaction, right? Nucleophilic attack and loss of leaving group. Well, what is the relationship between my alkoxide and my bromine? Do you guys remember the term anti-periplanar? Anti-periplanar. Does anybody remember this when we talked about anti-periplanar requirement for an elimination on a ring? Anyhow, it's something that we did cover in organic chemistry 1. Yeah, and so it's still a requirement. And so that's why a halohydrin, good thing is that you get anti-addition. So anti-addition. So again, the hydroxyl and the bromine are on opposite faces of the molecule. And so if they're both in an axial position, you can do this SN2 reaction, right? This is an SN2 reaction and make an epoxide just like that. And the mechanism is shown here. I just wanted to draw it for you kind of slowly. So remember that these groups, oxide or the alkoxide and the halogen, have to be anti-periplanar or it can't happen. Okay, it's not going to happen unless they're on opposite faces of the molecule. So you could say they must be trans in order for the reaction to occur. So if you took this compound, okay, if you had the hydroxyl pointing up, and if you had the bromine pointing up, like this, okay, you're not going to get any epoxide. No epoxide. Okay, will not work. They have to be trans to one another. Give me a thumbs up if you'll remember that. They've got to be trans. Even if you're like, I'm not sure if I'll remember it, but I think I'll remember it. That's good enough for me at this point. We're learning the subject. All right, so now you've got two routes to make an epoxide. And the good news is that they're both stereospecific. Okay, they're both stereospecific. If you start with cis, you get cis. If you start with trans, well, you end up with trans. Okay, and again, you know, a couple of semesters. I mean, this is years ago, probably. I had a student who was getting really frustrated with organic chemistry, and she would ask me all the time, "Why do I have to learn two methods to do the exact same thing?" And again, the rationale is that it's oftentimes these reactions are substrate specific, meaning one set of conditions might work well on one alkene, and one set of conditions might work well on another alkene. And so, a good organic chemist should have more than one way of doing any kind of reaction that they can, really. All right, so there you go. Preparation of epoxides. One of them involves a halohydrin, something you've seen before. We just do a little eliminate or a little SN2 reaction with the sodium hydroxide, and the other one, MCPBA, which again is a peroxy acid. That's something that you've seen before, right? That's just old hat. The section about enantioselective epoxidation, I'm not going to get into that right now. Let's see if we could try one of these questions here, and then we'll move on. So let's just try one, and then we'll try the other ones. Oh, maybe we'll try two. It says, identify the reactants that you would use to form a racemic mixture of each of the following examples. So all we need to do is a little bit of retrosynthesis here. If we're making an epoxide, that means it's got to come from a carbon-carbon double bond at this position where I have this blue oval here. So we need to have a carbon-carbon double bond, and you can see that the two phenols, the two aromatic rings, are on opposite faces of the molecule. So we'll put a phenyl here and a phenyl here. They are trans to each other. We see that we have the methyl group and the hydrogen are also on opposite faces of the molecule. And so if we had this molecule that I've drawn in blue, if we treated this with MCPBA, or if you did the halohydrin chemistry, treated with bromine and water, followed by sodium hydroxide, either one of those conditions is going to give you the product. It's going to give you a racemic mixture because the epoxide could be formed on the top face or the bottom face of the molecule, but it will work. So let's try the next one. Again, same rationale. We want to form a double bond, or we want to start with, rather, a double bond where I have the blue oval. So we're going to put a double bond like this. You can see that the cyclohexyl and the methyl are on opposite faces or sides of the molecule. So I'm going to put the cyclohexyl up here like this, and then I'll put the methyl group down here. And then we have a hydrogen here and a hydrogen here, and those are trans to each other. We can clearly see that. And so all we need to do is treat it with the exact same conditions, and we're going to end up with our product. That's all there is to it. The last one is kind of a fun one because you have to, you know, when you have two rings that are connecting like this, so if you have a ring like this and then another ring connecting like this, we call this spiro. So you would say that this is a spirocarbon here because it's got two rings attached to it. Anyhow, it's neither here nor there. But what would you need to do in this case? You'd have to have the double bond at this position, right? So you start with the double bond. You've got the methyl group down here. You've got the hydrogen up here. And then you just have to make the five-membered ring. 1, 2, 3, 4, 5. And you have to figure out where the oxygen is. So if you start from the back, 1, 2, 3, you'd go 1, 2, 3, and the oxygen would have to be at this position. If you put it where the fourth carbon is, that would be wrong. You've got to put it in that specific position, and then the same old conditions, either MCPBA or bromine and water followed by sodium hydroxide, is going to give us our product. So there you go. That's how you form an epoxide. And of course, you'd end up with a racemic mixture in each one of these cases, but we're not going to worry about enantioselective epoxidation. Again, you can read this if you want. I'll leave this as an FYI, where you can actually do the epoxidation on one side preferentially to another. And there's a whole set of different conditions that can be used to do that, but I don't cover it in this class. Okay. So that brings us to section 13.10, which is the last section of new material. After section 13.10, it gets into synthesis, which is not new. It's just a matter of using all the reactions that we've learned. And so what we're going to talk about here is the fact that epoxides are really powerful synthetic intermediates. I mean, they have a whole variety of uses. Why? Because they are reactive, right? They have a ring strain. If you take, has anybody here seen my Feezer model kit? I used to bring it to class sometimes. These models that are kind of silver and black. I don't know, you probably saw them in class sometimes, but if you try to make, yeah, that's right, Audrey, you've seen them. If you try to make a 3-membered ring with those models, it will break the model kit, okay? It will destroy it, okay? So the idea is that a 3-membered ring, like an epoxide, it's like a jack in the box. I mean, this thing is ready and primed to react. And so if you have a green yard, so let me just draw an epoxide like this. If you have a green yard, so let's say you have R minus, and then your MgBr is down here. This can act as a nucleophile and just hit that, right? And it will open up the ring, right? And then you'd end up with, you'd have R, and then you have 1, 2 carbons. So you'd go 1, 2, 1, 2, and then you'd have O minus or something like that. So it's really reactive towards green yards. A hydride, so you should know what a hydride is. It's a nucleophilic source of hydrogen. An alcohol, of course, you know what that is, and an alkoxide. So again, epoxides are really reactive. I guess that's my conclusion on this slide. And we're going to learn a couple of ways to open them. The first one, are you ready? Here we go. The first one is to just hit the epoxide with a nucleophile. Okay, so look deep into my eyes. What we're looking at now is nothing more than talking about nucleophiles. If you have, a nucleophile, it's going to attack one of the carbons of the epoxide, open it up, and you can make, for example, here, this is how they make, or one of the ways I think they make ethylene glycol, which is this molecule here, ethylene glycol, which is found in antifreeze. It's very sweet and delicious. It can be used to poison a loved one. Anyhow, so let's see here. It says opening of the ring is thermodynamically favored. Why? Because you might think, well, come on, O minus, that's not a good leaving group. No, it's not. But the reason why this reaction happens is because it relieves the ring strain. That's the whole rationale here, okay? So if you think about, I can't do an SN2 on just a plain old ether. You had to protonate that. I would say absolutely. I will not argue with you on that. Look, the reason why is all based on thermodynamics. If you just have a regular old ether, the activation energy to pop that open with just a nucleophile like hydroxide is way too high. Whereas when you have an epoxide, you have so much ring strain that it raises the potential energy, and so your activation energy is actually pretty low. It doesn't take that much, to open it up because it's thermodynamically favored, right? If you look at the red curve, that's an exothermic reaction, but if you look at the blue curve, that's an endothermic reaction. So with all that in mind, if you're wondering, well, what kind of nucleophiles can I hit my oxirane or my epoxide with? So here's your epoxide. Okay, I'm going to stop and take a drink of coffee here, just so I can stop talking for a split second here, because I want to tell you something about this slide. I've never said this before to a class, but I'm going to say it to you guys. There is a lot of information here. It doesn't look like much, but there's a crap load, pardon my language, of information on this slide. There's a lot of information here. So check this out. If you were to hit the epoxide with an alkoxide, so this is an alkoxide, in that case, you end up forming an ether, right? And this end is going to end up forming an alcohol after you protonate it. If you were to hit it with cyanide, so this is sodium cyanide, so you should know that Cn minus, right, is a good nucleophile. So this is cyanide. You make a nitrile. And what's interesting about this is you've made a carbon-carbon bond, right? This is a carbon, this is a carbon. So that's kind of interesting. The next one, this ion, SH minus, this is called hydrosulfide. So hydrosulfide, okay. Hydroxide is OH minus, hydrosulfide is SH minus. In that case, you would make a thiol. All right, and we're still not done. If you hit it with a green yard, you're going to make a carbon-carbon bond, so carbon-carbon bond. And then if you hit it with a hydride, you hit it with a hydride like lithium aluminum hydride, you're going to add a hydrogen or a proton, whatever you want to call it. All right, and notice that in each case you also made an alcohol, right? You end up with an alcohol 2 carbons away from the new functional group that you installed. I guess the first 4 are ether, nitrile, thiol. Those are functional groups. A carbon-carbon bond, that's not a functional group, and a proton, that's not a functional group, but you get my drift, right? You have 2 carbons in between every time. And so if you think about new things here, everything here is new. I've never showed you, I guess we talked about how to make a nitrile when we did an SN2. Thiols, I guess a little bit with SN2, but there's a lot of information on this slide, okay? So if you're wading through the practice problems tonight or tomorrow or something, and you're like, where did a nitrile, where did that come from in this chapter? Well, there you go. Or where did a thiol, I don't remember a thiol. Well, here it is. And so to move forward from this, we have to keep in mind that not only can we do these reactions, but here's where it gets really crazy, is that these reactions are regioselective. So that means they're going to preferentially attack one carbon over the other, depending on the situation. And they're also stereoselective. And so if we have a stereocenter at one of these carbons, that's going to matter as well. Are you ready? Again, right now, we're just talking about nucleophiles. We are not talking about acid-catalyzed opening. So when you're dealing with a nucleophile, here's the rules for regioselectivity. It says the epoxide ring opening is SN2. So what does that mean? Come on, if it's SN2, it's just going to hit the least hindered carbon. That's it. That's all. That's the rule. So if we look at these 2 carbons, if I circle this carbon in red, the other one has the green box on it. Well, the one in green is less substituted, so that's where the nucleophile is going to attack. And so if you're wondering, could I just draw a mechanism like this? Nucleophilic attack, loss of leaving group, and then there's a proton transfer in the step with the water. Absolutely, that's the whole mechanism. And so I want you to know this mechanism. Okay, very important mechanism in this class. Okay, the nucleophilic ring opening and then the proton transfer. Now, in terms of stereoselectivity, we already covered that if you were to attack this molecule with a nucleophile, you see where the yellow carbon is? That one's the more hindered carbon. The one where the green box is the less hindered carbon. Well, where is the nucleophile going to attack from? Is it going to attack from the most hindered face or the least hindered face? It's going to go to the least hindered face. So do you have a proton going down here? Yes, you do. However, what's smaller, a proton or an oxygen? The proton is smaller, and so the nucleophile, the nucleophile is going to attack from the bottom face of the ring and open it like this, right? If you were to draw the chair, you have to say it with that accent, of course, okay? If you were to draw the chair, so here's my epoxide pointing up like this, here's my proton going down, and here's my methyl group, I'll just draw it like this going down, right? The nucleophile, I'll try to draw it the same way, and I'll never ask you to draw a chair like this, but the idea is that the nucleophile is going to attack from the bottom face because it's the least hindered of the 2 faces. Oh, jeepers, I hope you can follow them. Give me a thumbs up if you can follow me. I'm going to try to move this just so you can see it a little better, maybe. We put it over here. Is there room for it there? Yeah. Does that make some sense to everybody? It goes to the least hindered face or least hindered side, and then it also attacks from the least hindered face. All right. And so now our nucleophile is going to be pointing down, and our hydroxyl group is going to be pointing up, as you see here. So what's happening? It's an SN2 reaction, and we know that SN2s proceed with inversion of configuration. All righty. There we go. So we've covered stereoselectivity and regioselectivity in terms of our ring opening with a nucleophile. So we're going to dust our hands off and stop there. That's the end of nucleophiles. I think the next slide deals with acid catalyzed. So if you're following along with me, and I know you all are, if you start here, we're starting with nucleophiles. So nucleophiles, okay, and that's covered on this slide this one, so 39, 40, 41, 42, 43, and that's the end. So end just nucleophilic attack. Nucleophilic attack. And now we're going to start with something that's different. It's in the same vein, but there's a different set of rules here. Now we're getting into acidic, okay? Acidic ring opening. So now we don't just take a strong nucleophile and hit the ring. Now we're going to look at using weaker nucleophiles. And the way that we promote the ring opening is that we protonate the oxygen first to convert it into a better leaving group. Okay? So again, we're switching gears here. So everybody with me? Switching gears from nucleophiles to acidic. Cha. And the reason why I'm making a big distinction here is because the regioselectivity is going to be different in this section. This is where it gets really interesting. Okay? So acidic conditions, let's take a look. Acidic conditions can also be used to open an epoxide, but now with a weak nucleophile, okay? What would you use? You'd use HCl or HBr as your acid. This would be your acid. And water and an alcohol, those are what? Those are weak nucleophiles. Okay, so if I have a weak nucleophile, it's not just going to crack open an epoxide. I have to protonate it first. So now I've converted this into a better leaving group, and now a weak nucleophile, like let's say chloride or bromide, those are, yeah, they're decent nucleophiles, but weak bases. But anyhow, so now we have our nucleophile that's going to come in and do our SN2. Give me a thumbs up if you follow me on this mechanism here. Any questions about this mechanism? And I realize you're probably tired at this point, but this is important. Okay, I understand, of course, in the summer, it gets kind of long in the tooth here. It's, we get into the second hour of, oh boy, another reaction, Mr. Young. Okay, so just bear with me just a couple more things, then we'll be done with new material for this chapter. So look, if we have the acid catalyzed, remember that when you have a square brackets, that means a catalyst. So if you have a catalytic amount of H+, so a proton, so just a catalytic amount of acid, and water or an alcohol, right? The first step is that you're going to protonate. Son of a gun. First step is going to be that you protonate, and then a molecule like water can come in as a nucleophile and open up the ring, right? Or an alcohol could come in and it could open up the ring. But again, since these are weak nucleophiles, water and alcohol are weak nucleophiles, you have to have an acid catalyst. Okay, so maybe I should have written here acid catalyst like that. And in fact, ethylene glycol is made this way. They take ethylene oxide and just treat it with sulfuric acid and water. So here's the mechanism, and you need to know this mechanism. Okay, when you just take an epoxide, you protonate it, that converts the oxygen into a better leaving group. You have a weak nucleophile like water, and it's going to attack. Okay, we open up the ring, then we get a proton transfer in the end, and in this case, we make a glycol. Remember, a glycol is just a diol. Okay, it's just a compound with 2 hydroxyl groups. Okay, so the next 3 slides are going to be crucial to your understanding of acid catalyzed ring opening. Here we go. This one here. Under acidic conditions, the nucleophilic attack still occurs at the less substituted carbon if you have a primary and secondary carbon. Okay, so if we look at this molecule, this carbon is primary. Why? Because it's attached to 1 carbon. The carbon on the right-hand side is secondary. Why? Because it's attached to 2 carbons. So to rehash, if you have a primary and secondary carbon, the nucleophile is going to attack the least hindered carbon. So first you would protonate, and the first step, right, you'd form this, and then X minus, your nucleophile, would come along and it would attack at the least hindered carbon, and you'd end up with this molecule here. However, this is where it gets really interesting. Okay? Interesting. And I know that not everybody finds this interesting, but I can't think of a better word right now. If you have a primary and tertiary, it attacks the tertiary carbon. And if you're going, I hate this class, why would it attack the most hindered carbon that goes against everything you taught me? I'd say, yeah, in a way, it does. Okay. So again, in the first step, you'd protonate the oxygen. Okay. And now your nucleophile is going to come in and it's going to attack at the more hindered carbon and crack open the ring like this. And again, you're probably, I'm sure you're wondering, why would it do that? Right? Of course, somebody asked me one time if you had secondary versus tertiary. Well, if tertiary wins over primary, it's definitely going to win over a secondary too. So if it's secondary and tertiary, you're going to go with the tertiary. All right. So let's cover the rationale. Let's cover the why does this happen? Here's the answer. Since the epoxide is cationic, right? Once we protonate, so here's the cationic species, okay? Now, if you're like, well, you didn't draw it like that. You had it, it looked like this, okay? No problem, okay? But what they're showing you, I'll just put, it's the same thing as this. The rationale, it's based on an electronic effect, okay? Based on partial positive charges. So since the epoxide is cationic under acidic conditions, electronic effects result in the carbon-oxygen bond to the tertiary carbon being much weaker, right? Because if you think about this bond in yellow and this bond in green, right? So that's this bond versus this bond. Which one is going to be more comfortable with carbocationic character? The carbon that is attached to the bond in green is going to be much more comfortable than the one attached in yellow. And so since during the transition state, the positive charge passes through the carbon that's more substituted, that is the rationale as to why we get nucleophilic attack on the tertiary carbon. Am I going to ask you to write an essay on that? No, that's not happening, but that is the rationale. So to rehash, when we have primary versus secondary, the dominant effect is going to be sterics, okay, the steric effect. If you have primary versus tertiary, we can put here, or secondary versus tertiary. In that case, the dominant effect is going to be the electronic effect, and it's always going to go to the tertiary carbon. All right, give me a thumbs up if you'll remember that for me on your quiz. You're like, yeah, when I see an acid, I'm going to know that if it's primary and secondary, it's going to go for the least hindered carbon because of sterics. When I have a primary and tertiary, or a secondary, or whenever I have a tertiary, it's going to go for the tertiary based on the electronic effect. Now, the textbook is going to go into more detail on this electronic effect. And I know you're all going to take the time to read this section. So read that part, and it will give you a beautiful rationale for why that happens. Okay, so let's take a look at this here. It says under acidic conditions, inversion of configuration is still observed, right? Why? Because it doesn't matter which carbon is attacked, it's still an SN2 reaction. And when you have an SN2, you're going to have inversion of configuration. So if we look at this molecule here, what's going to happen is after you protonate in the first step, right, you form the oxonium ion, what's going to happen is the alcohol is going to attack at the tertiary carbon, and that's this one that I'm highlighting, or the one that's highlighted in green. Right, let me use my blue pen. This one is tertiary. This one is secondary. So the tertiary is the winner. All right. And if you look at the two faces of the molecule, which one is less hindered? Well, on one face, you've got a little old CH3 group, and on the other one, you have an oxygen, right, as part of a whole ring system. And so our nucleophile is going to come in and it's going to attack the least hindered face. It's going to attack from the bottom face. And when that opens up the ring, it's going to push the methyl group. Let me use my blue pen. It's going to push the methyl group from being down to going up. And if you're wondering, oh, I'm never going to remember that, all you have to remember is that it's an inversion of configuration. Why? Because this is an SN2 reaction. Nucleophilic attack followed by loss of leaving group. There's nothing new under the sun here. So there's no new information here, really. So with all that information, this question here, 13.16, says for each of the following reactions, predict the product and draw a mechanism for its formation. The next question says, for 13.18, says for each reaction, predict the product and draw a mechanism for its formation. So you can see that these two questions have some differences. If you look at 13.16, everything that's in here whether it's the this is called a thiolate. So when you have this is called a thiolate. Whether you have the thiolate or the hydride or the ethyl oxide, these are all what? These are all nucleophilic ring openings. So nucleophilic. Okay, no acid required. But if you look at question 13.18, you have an acid catalyst for both of the questions. So these are acid catalyzed ring openings. Acid catalyzed. And so you've got to be able to do both. Well, with all that in mind, let's take a look at the first one. Okay, we'll try a couple of these, and then maybe we'll take a break and you can try a couple on your own. There we go. All right. So let's say we have our thiolate here in the first step. Well, if I highlight this carbon in yellow and this carbon in green, can anybody tell me which one of these carbons is going to undergo the nucleophilic attack? Yeah, the one in yellow, right? Because it's the least hindered. Absolutely. You're all 100% correct. So what do we have? We have our nucleophilic attack. And then we're going to open the ring. So we're going to count the carbons very carefully here. Okay. And I'm not doing any nomenclature here, but look, we have carbon 1, 2. So here is carbon 1. We'll label this carbon 1 and this carbon 2. All right. So what's attached to carbon number 1? Attached to carbon number 1 is going to be a sulfur and a methyl group. And attached to carbon 2, I'm going to have a methyl group that's coming out, and I'm going to have my alkoxide, right? Because this is just the first step. In the second step, what's going to happen is going to be a proton transfer. So I'll draw my water molecule, and this is going to grab a proton from the water like this, and that's going to give me my product. So I end up with something that looks like this. I have a stereocenter here. And there you go. So you see that you've made two functional groups, right? You have an alcohol here, and you have a sulfide down here. So wowie wow, two functional groups at the same time. All right, it's getting interesting here. Let's try the next one. If we have lithium aluminum hydride, if we draw the aluminum hydride ion, it's going to look like this. Okay, so we get a nucleophilic attack like this and a loss of leaving group like that. So again, I'm going to number these carbons as carbon 1 and 2. I didn't finish it up here. But anyhow, so if I draw a line like that, I have carbon 1 and carbon 2. So carbon 1 in the oxirane already has 2 hydrogens attached to it. So you're going to add a third hydrogen. If you want to draw it in, you can, but it's just a methyl group, so I'm going to leave it that way. And then you're going to have, oops, black pen. Then you're going to have this methyl group like this. Then you're going to have the oxygen like that. Then you have a water molecule, which is going to affect the proton transfer. So we add that's not a very good curved arrow. Wink, there we go. So we're going to take on a proton. And what's interesting with this molecule is it's got no stereocenter. Okay, this is just isopropanol. So there you go. All right. So I'm going to let everybody try the next one on their own, and we'll come back to it if we have time. But if I just highlight this carbon in green and this carbon in yellow, could anybody tell me which one of those two carbons is going to undergo the nucleophilic attack by the ethyl oxide? Cha, you're all 100% correct, right? It's going to do a nucleophilic attack like so. So we're going to crack that open. We can number our carbons, 1 and 2. I'm going backwards now, aren't I? So whatever, doesn't matter. So I'll call this 1, I'll call this 2. So on carbon number 1, you're going to have the OET, so you're going to have an ether that you formed here. Then you have the alkoxide up here. You've got your phenyl in the back, so I'm just going to write pH for phenyl. And you've got your ethyl group over here. And then the next step is the proton transfer. So we throw in our water molecule. You grab that proton. There you go. It makes that sound too when you do it. So there you go. So you have the alcohol. You also formed an ether. And you have a stereocenter in here. Is this, as we say in French, c'est pas beautiful, so? All right. So there you go. So strong nucleophiles do not require acid. So let's put in here. Friends don't let friends. No, we'll put in here. Let's change this. Strong nucleophiles do not require acid. I didn't really have to capitalize require, did I? But anyhow, do not require acid, all right? So if we look at an acid catalyzed ring opening, here we have an acid catalyst. So what's going to happen? It says draw a mechanism for the formation. So let's take a look here. The first step is we have our sulfuric acid. You know what? I'm going to draw a simplified version of this mechanism and just, I was going to draw H+. I can't do it. I can't bring myself to do it in front of you guys. Everybody's watching, so I'm too embarrassed to make a shorthand. So we protonate in the first step. We end up with this guy. So now we've converted the oxygen into a good enough leaving group. The some old piddly weak nucleophile like water can come in and attack. I have over here a methyl group. Okay, here's the $1 million question. If I highlight this carbon in yellow and this carbon in green, where is the nucleophile going to attack? Cha, right? Thanks, Maria, because it's the tertiary carbon. Absolutely, yes. Right, because it's an electronic effect. So electronic effect. Okay, there we go. So where's my water molecule? Where's water when I need it? Here we go, there we go. So it's going to do a nucleophilic attack. Here's this leaving group. So remember, this is an SN2. So there's going to be inversion of configuration. So these two groups that are pointing down, they're going to go up, right? Because they're being attacked from the bottom. So we get inversion of configuration. So when we draw, it doesn't mean the methyl and the ethyl are going to switch being a dash and a wedge. It means the methyl, instead of pointing down, now it's going to be pointing up. And the ethyl is going to be pointing up. And the oxygen from the water molecule is going to be pointing down. Of course, it's still protonated. Then you have this methyl group coming out here, and you have an alcohol over here. So for the very last step, what's going to happen is a water molecule is going to come along and it's going to take this proton and you're going to end up with a diol. So you end up with, where's my pen? You end up with something that looks like this. So you have the methyl group here, ethyl group here, alcohol here, the other alcohol here, and this methyl group is going to be coming out just like that. And there you have it, man. So we covered acid catalyzed ring opening, and we covered nucleophilic ring opening where there's no acid catalyst. All right, I'm going to leave this one maybe for next class, and we'll come back to it. The section on thiols and sulfides, it says skip. I don't like skipping this entirely because so many of you are going to move on to biochem after this class, and sulfur shows up all the time in biochemistry, so I don't think it's unimportant. It's just that the ACS doesn't ask a lot of questions about sulfur, but you should know what a thiol is. You should know that it's the sulfur analog of an alcohol. Another thing, this is probably something you've never heard before unless you read the book, is that a thiol, right, which is RSH, okay? We also call them mercaptans, and you're like, what the heck is a mercaptan? The reason we call it a mercaptan is because it captures what's the word? It captures mercury. So mercury, it captures mercury. It binds with mercury. I also want to cover a couple of other things. So if you have a sulfur with a negative charge like this, I told you that this is called a thiolate. I just want to bring up the word, a thiolate. It's also called a mercaptide. So mercaptide. And the other thing is, you guys know what a hydroxyl group is, right? You know that this is called a hydroxyl, or sorry, a hydroxide, my mistake. So hydroxide, like this. If you have SH minus like this, we call that sulfhydryl or hydrosulfide sometimes. So you can call it a sulfhydryl group like that. Anyhow, just a little bit of nomenclature there. Anyhow, and I'm going to leave the rest of 13.11. I'll leave that as an FYI. So make sure you read it. It's very short. Believe me, the section is very, very short. And that brings us to the very last section that is of relevance to us, I think, in this chapter, which is the section on synthesis. So what you're going to see as a recurring theme in Chemistry 3111, in case you haven't noticed already, is that we learn a whole bunch of reactions and then we practice using them over and over, and designing new syntheses and things like that. So we're going to take a break before we come back to this. So yeah, why don't we take a little break and then we'll come back and we'll talk about some syntheses just to get the ideas flowing, because we don't have class again until Wednesday. So I want to go over some of the rationales here before you step into the synthesis. You should hear a little bit about it from your instructor.